Okay, so we are picking back up for vision. This is part 2 of vision. We're in chapter 3 of the Rathus text covering sensation and perception. And can't stress this enough. Human beings, we are visual. We are a visual species, meaning a lot of our cortex, a lot of our cognitive effort is put towards seeing things. Granted, we may not have the best vision, of other species. I mean, we looked at the color spectrum, a visible light spectrum last class, and we see a very finite, very small portion of that, but we still rely tremendously on our vision. So we're going to keep moving forward with that. This will actually this portion of the discussion on vision will be mostly focused on sort of how do we organize all of these stimuli that we come into contact with visually. I mean, the moment you open your eyes in the morning, you are bombarded and flooded with images, with light and images. And so, how do we organize? How do we make sense of this all? And so we're going to look at some interesting phenomena related to vision. So one of the first things we're going to talk about are after images. You're going to need to get your textbook out. Maybe as I'm going through this first slide, go ahead and start grabbing your textbook, and you'll need to turn to page 73 in the Rathus text. We're looking for figure 3.6. But if you've ever closed your eye, if you've ever looked at an object for a good amount of time, then maybe you take your eyes away, or maybe you close your eyes, but yet you can still sort of see that object, that sort of image. It's almost like it's momentarily burned into your eyes. This is known as an after image. It's a persistent sensation of color, followed by the perception of complementary colors. After looking at an image for a while. So I actually want us to try this. Go ahead and we're going to flip over to the next slide. And so there's something wrong with our American flag here. So what is wrong with this flag, and maybe how can you fix it? What I would like for you to do is, in a moment, I'm going to give you some directions that I'm reading from the text, and you can pause the video and do these yourself or whatever. But after I read the directions, go ahead and pause the video and try this for yourself and see if you get it to work. It's a really fun activity. So hold a sheet of white paper close to the image. Focus on the black dot in the center of the flag. So this black dot here, you can see my mouse cursor going over it. Go ahead and focus on the black dot for at least 30 seconds. Now move your focus to the sheet of paper. The after image on the paper beneath will look familiar. So go ahead and pause the video and see if you can get this to work. Okay, welcome back. If you did this right, you should have seen an after image of the American flag with the right colors, because yellow, black, and green, those are all of the opposite or complementary colors to red, white, and blue. The black would be the black we would fill in with the white stripes, the green with red, the stars would be white, the yellow would be blue. So if you did this after image trick correctly, you should have seen the red, white. You should have seen Old Glory, red, white, and blue. If you didn't, that's okay. Sometimes it took me a couple times the first time I tried this thing. So maybe just pause the video again and try it again, or if you'd like. But really neat stuff. So a couple of theories of colored vision, like why we see in colored vision, and kind of relating back to this idea of after images. You have one theory, the trichromatic theory, sometimes just called three-colored theory, or something not so fancy. Trichromat meaning three. According to this theory, we have three different types of cones. Remember from the last video, we have cones that are responsible for regulating color vision. According to this theory, we have three different types of cones that are sensitive to particular colors like red, green, and blue. And through those combination of those cones is kind of how we develop all of the rest of the color spectrum. Red, green, and blue are kind of the pillars of our color vision. Similarly, there's opponent process theory, which kind of, I'm not going to say either one of these theories is more right or wrong than the other. They're just sort of trying to explain the same phenomena of colored vision. And opponent process theory conversely says, well, we have these three types of color receptors. Rather than just being red, green, and blue, they're more like kind of opposite pairs. So red, green, blue, yellow. And I want to say there should be one for black, white, but I don't think it's listed here for whatever reason. So there's sort of opponent process theory is kind of adding on to trichromatic theory, but they're sort of talking about the same thing. At these receptor cells, maybe we have these different types of cones or receptor cells that are sensitive to different colors. And that seems to make sense. That seems to be the leading idea behind color vision currently in psychology. What about color blindness? Well, color blindness, we can use both of these theories to sort of explain color blindness. Now, somebody who has full, normal colored vision would be considered a trichromat. They have the red, green, the blue, yellow, the light, dark. Those cones are working just fine. Someone who is considered a monochromat, they are totally colorblind, meaning they're seeing in black and white. If you've ever seen that movie Pleasantville with Tobey Maguire, it's like living in the 1950s where everything's black and white, Beaver Cleaver style. Dichromats, on the other hand, are partially colorblind. They may have a tough time either seeing blue-yellow or red-green, but not both. Now, interestingly enough, I think the data and research shows that men are more likely to be colorblind than females. So if you're listening to this and you're a male and you're colorblind, sorry, you got the short end of the stick on that one. Interestingly enough, there are now glasses that you can order off of the internet that can correct color blindness. I have a buddy of mine I play fantasy football with who is colorblind, and our friend group put some money together and bought him those glasses, and he got to see color for the first time, and it was a really, really neat thing to see. So you can find YouTube videos like that as well. So this is what color blindness. If you were colorblind, you would have a tough time seeing, the fact that this says 6. There's a 6 here, and there's a 12 here. If you were colorblind, these are kind of tests that you can take to see if you were colorblind. I think you can do these online as well, but this is a typical test item for if you were colorblind. All right, so now we're getting into the part of the chapter where we talk about how we organize all this stuff. How do we organize all of the sensory information that strikes our eye from the moment we wake up? And it's a very complex process. It happens very quickly, happens very rapidly without us really knowing it. So let's kind of talk about that process. It is an active process. It involves, our perception. So we take in all this information, but how do we make sense of it? Oftentimes, that's based on our prior knowledge, expectations we have, motivations, emotions, all kinds of factors that are in play, in determining, once we see something, how do we interpret what we see? So that's where we're going with the rest of this chapter. Is we see it, now what does it mean? So the perceptual is a very active process, again, as I mentioned, but the actual process of detecting the light, the sensation itself, is a mechanical process which we outlined in the last chapter. Light hits the eyes, travels to the eyes, down the optic nerve to the occipital lobe, and back out again. So we're going to be kind of looking at both. We're now switching gears, and looking at more of the active process, the cognitive process. So what's going on in this image? Go ahead and pause the video and see if you can figure out what's going on in this image. So welcome back. If you pause the video, you should be able to tell from this picture, that this is a man riding a horse. You can see the man here, his body. This is the horse, 1 leg, 2 legs, start of a 3rd leg, a 4th leg. Now, your brain can sort of fill those gaps in automatically without having me tell you that, hey, this is a man on a horse. For the most part, I think most of us can look at that and say, fill the gaps in. And this is what is known as the Gestalt principle of closure. And we sort of talked about Gestalt psychology a little bit in chapter 1. But the idea behind Gestalt psychology, a German perspective in psychology, is that, how do we organize all this sensory information, specifically visual information? And a lot of it is done automatically by our brain. We fill in the gaps. Even if things are missing from an image or picture, we can kind of fill in the rest ourselves. And it really goes to show how powerful our minds really are in terms of like visual imagery and visual stimuli. So this is one, the principle of closure. We'll talk about some more in a moment. But this whole idea of being able to organize visual information, perceptual information, how do we integrate all of these bits of sensory information into something that it's meaningful? And here's another example: is the figure ground perception. It's where you have an ambiguous relationship could lead to an unstable perception. That may not make a lot of sense right now, but it will make more sense here in just a moment. Look at, this is called the Rubin vase exercise, and it's in figure 3.9. It's on page 75 of your text. So if you look at, maybe if you look at part A, your mind can kind of flip back and forth between seeing a vase or seeing two faces looking at each other. This is the vase, this is what a vase is, or sometimes, you can think about it, your mind can kind of switch back and forth and see a face. But what about part B? Maybe part B, you're much more likely to see the vase, whereas with part C or number C, or letter C, I should say, not number, you're maybe more likely to see the profile. It's all about kind of where things fit into this figure-ground relationship, figure being the forefront and ground being the background. And depending on where it's positioned, it makes it, you see differently. You kind of flip back and forth here on A, you see one thing on B, and you see only one thing on C. So changes your total, it could change your perception of this simple stimuli. So more Gestalt principles or rules, I'm going to kind of go through these. You have proximity, similarity, continuity, common fate, and closure. We've already seen closure. Let's take a look at a few others in the next slide. Let's take a look at proximity. Things that are together, we're more likely to group things together. We're more likely to think, hey, these things are connected because they have a proximity to each other. You're more likely to organize these into rows like X's and circles, because of the similarity. The X's are similar, the O's are similar. Continuity, that the line continues despite having the circle in the way. Your mind can kind of fill in the gaps on its own. And then closure, we can fill in the gap. We know this is a circle even though it is somewhat incomplete. Kind of like the picture of the man on the horse in the previous, on figure 3.8. So how do we, when we're processing information, we use sort of one of two methods. We either use top-down or bottom-up processing. Top-down processing is using contextual information or prior knowledge to understand or organize information into a meaningful way. Bottom-up processing is where we are forming an image, we are developing the pattern kind of on the spot, we are forming this new pattern on the spot. And I think of this as, I know we're talking about vision, but I think of top-down versus bottom-up in terms of music. The first time you hear a song, the very first time, you're using a lot of bottom-up processing. You have to really listen to the song. You don't know the words, so you can't sing along with it. You don't know the beats. Maybe it's kind of hard to dance with it too. You got to really kind of listen for the first time and really process that information, develop the patterns, develop the recognition. But over time, after you've heard the song 5, 10, 15, 20 times, you now can sing to it. You can dance to it. You can even think about it in your mind without even really hearing the song. Then you're switching over to top-down processing. You're using prior knowledge and contextual information. And that's what we do with all of our sensory information, not just vision, not just hearing, but especially with all of these things. Sometimes if we've never encountered something before, we have to rely on this bottom-up processing. We have to build from the ground up. But if we have prior experience, then we can kind of build top-down. Motion, how do we perceive motion? It is a perceptual event. It's, the change, the relative position of objects, persons or objects. There are some illusions that make it seem like things are moving or not. If you ever made one of those little books when you were a kid in school, if you ever drew, in a book on, you drew a stick figure on one page, drew the same stick figure kind of doing something different on the next page, and with enough time, you flip through those pages, it kind of looks like the stick figure's in motion. That's what we mean by an illusion of motion. Here's another example. It's called stroboscopic motion. I don't actually have a video to show you here, but this is what it might look like from figure 3.11. It's depicted on page 76 of your text. In a motion picture, viewing a series of stationary images at about a rate of 22 frames per second provides an image of an illusion of movement when there really isn't. Really, it's just the same. It's multiple images being sped up fast enough that it looks like it's moving when it's really not. Depth perception. We can perceive depth with either a single eye or with both eyes. Obviously, depth is better with both, but if for something were to happen to you, God forbid, to one of your eyes, you still can perceive depth. You can perceive things like perspective, relative size, clearness, overlapping, shadowing, the gradient of the texture, motion parallax, and this will make a little more sense here in a moment. This will make a little more sense with some examples. Overlapping, you can cover up your eye, you can cover up one of your eyes and see, you can tell the overlapping circles. You can see that this lighter blue circle is overlapping the darker blue, and the green is overlapping kind of this kind of pinkish, whatever color you want to describe it as. Shadowing as well. You can tell that you can see shadowing for this image here, but not on this one here, even with only, by covering up an eye and using one eye. We also have binocular cues, using both of your eyes to perceive depth. If you're not aware, you have what's known as a retinal disparity, where you have two eyes, obviously, and both of those retinas on your eyes are developing a picture, if we're using the metaphor of the camera. And each one of those is a different image. It's slightly different. It's from a different perspective, obviously, because it's on one side of your nose versus the other. And how we see is a convergence of those two images coming together. That's what your occipital lobe does. It puts those two together to where they make sense, and we don't see cross-eyed or see all double vision or whatever weird we see normally. Additionally, there are also perceptual constancies. We are able to tell that certain things are constant despite our relative position or despite other conditions being changed, like size constancy, color constancy, brightness constancy, and shape constancy. And here are some examples of those that'll make sense. If you look at figure 3.13, is the woman's hand really twice the size of her head? We can tell, based on depth perception, we can tell that even though her hand looks really big right here, it's not twice the size of her head. It may look like it in this picture, but we know that, if we bring her hand a lot closer to her face, it's nowhere near the size. Brightness, the orange squares, which one is darker? Which orange square is darker? Well, neither of them are, because in fact they're the same color, but because this side is darker, you might be prone to think this square is darker, but it's not. Shape constancy. What is the shape of the cover of this coffee cup? If you thought it was a circle, this coffee cup here, then you're right. You're filling in the shape despite not being able to see the whole shape. You can tell that this guy isn't drinking like an ellipses or a crescent moon-shaped coffee cup lid. That would be really weird. Our brain fills in that information without us knowing it. A couple of other examples. These are the Herring-Helmholtz and the Mueller-Lyer illusion. Are the lines in the example on the left, are they horizontal, straight, or curved? Your brain your brain wants to look at these as if they're curved, but they're really not. These are straight lines, but your brain initially kind of tells them they're curved because of the way these lines work. And the Mueller-Lyer-Helm illusion. Which one is longer, this line or this line? Well, your mind might want to think this one is longer because of the arrow pointing down, but in fact they are the same size. We just manipulated the arrow points. So that is it for vision. We're going to stop here. I feel like I've overwhelmed you too much with stuff on vision. Let's take a break before we move on to sound. Our next video, I think we're only going to do 2 more videos, sound and then the other sensations. So we'll stop here and resume with sound. So thanks for checking in, and we'll talk soon.